Hello bachcho, welcome to the class. So today we are going to tackle a really important topic from our alternating current chapter. What happens when we apply AC voltage to a pure inductor? Now don't worry about it at all. I promise that by the end of this session, the concept will be absolutely crystal clear and you'll feel so much more confident for your exams.
Chala, let's begin. But you know what? We're not going to start with some scary formula. No. Instead, let's start with a simple question, something you've probably seen in your own house. Have you ever noticed this? You go to flick a switch off, especially for something heavy like a motor or an old fan, and you see a tiny little spark inside the switch. Why does that happen? Well, the answer lies in a component that absolutely, completely hates change. And that, bachcho, is the hero of our story today. That component, as you've guessed, is the inductor. Now, to understand it properly, we first need to get a feel for its core personality. You can think of it as having electrical inertia. Just look at this comparison here. A resistor. It's very simple, very obedient. You apply a voltage and the current flows instantly. It's just like pushing water through a normal pipe. But an inductor is different. It's like the pipe is filled with a very thick, heavy liquid, maybe like honey or something. When you start to push, it takes a little time for the flow to actually begin. And when you try to stop, it wants to keep flowing for a moment. This is the main point. An inductor resists the change in current, not the current itself. Yeah, this flywheel analogy is perfect. Think about it. You can't just make a heavy flywheel spin at full speed instantly, can you? It takes effort, it takes time, and once it's spinning really fast, you can't just stop it with a snap of your fingers either. That's inertia, right? Well, an inductor is the electrical version of this flywheel, but for current. Okay, so we've got this idea of inertia in our heads now. Let's translate this into the proper language of physics for our AC circuits and see exactly what it does to voltage and current. This, bachcho, is the official NCERT formula, and it is the key to everything. You have to look at it very, very carefully. The voltage V is not proportional to the current I, not at all. It's proportional to di by dt, the rate of change of current. So what does this mean? It means the voltage is at its maximum, not when the current is maximum, but when the current is changing the fastest. Please remember this. Now, don't get scared by the math here. It's actually very simple. Let's just build it up, step by step. First, we just assume the current is a nice, simple sine wave. Okay. Second, we find its rate of change, di dt. Now, from your basic calculus, you know the derivative of sine is cosine. Simple. Third, we just plug this result into our voltage formula. And what do we get? We find that the voltage is a cosine wave. So what's the big deal? What's the relationship between a sine wave and a cosine wave? Well, a cosine wave is simply a sine wave that starts 90 degrees earlier. So, the most crucial point, the one you absolutely must remember, is this. In a pure inductor, the voltage reaches its peak first, and then the current reaches its peak 90 degrees later, which is a quarter of a full cycle. So we say that the current lags behind the voltage. And this is how we show it visually, using phasors. A phasor, if you remember, is just a rotating vector that helps us see the phase relationship. So if we place the current phasor I flat along the horizontal axis, the voltage phasor V will be pointing straight up, a full 90 degrees ahead of it. And as they both rotate together, the voltage is always at quarter turn ahead. Okay, so this opposition to the change in current, it has a special name. We call it inductive reactance, and we write it as X with a subscript L. It's measured in ohms, just like resistance, but there's a huge, huge difference. Look at the formula. X_L equals omega L, and since omega is 2 pi f, it means the reactance actually depends on the frequency f. So the higher the frequency of the AC, the more the inductor is going to oppose the current. All right, let's make this concept completely solid by solving a very simple numerical problem. You know, the kind you often see in your board exams. Here's the problem. We have an inductor, and we have an AC voltage source. All we need to do is find the inductive reactance and the peak current. That's it. Let's just break it down. Step 1. We look at the voltage equation. V of t equals 20 sine 100t. From this, we can clearly see that the peak voltage V0 is 20 and omega is 100. Step 2. Now we find the reactance. We use our formula, XL equals omega L. So that's 100 times 0.1, which gives us 10 ohms. Easy, right? Step 3. Finally, we can use Ohm's law, but for AC circuits. The peak current, I0, is just the peak voltage V0 divided by the reactance XL. So 20 divided by 10 gives us 2 amps. See? Simple as that.
Now, bachcho, this section is very, very important. I want to talk about two silent killers. These are very common mistakes that students make in their exams, and I really want you to avoid them so you don't lose any marks. So please pay close attention.
Okay, mistake number 1. Students hear the word that an inductor opposes the current, and they automatically think opposition means 180 degrees, like moving in exactly opposite directions. This is completely, totally wrong. The correct fact is that they are 90 degrees out of phase. They are perpendicular. Now here's a super useful trick to remember this for your entire life. E-L-I, the Iceman. Just focus on the first part. E-L-I. E-L-I. In an inductor L, the voltage, E, comes before the current, I. See? E-L-I. This simple trick will save you from making a really silly mistake in the exam hall. And here's the second big misconception. Because reactance is measured in ohms, just like resistance, many students think it behaves exactly like resistance and consumes power and generates heat. But the reality is that a pure inductor consumes 0 average power. It's not a resistor. Think of it as an energy storage device. In one part of the cycle, it borrows energy from the source to build up its magnetic field. And in the next part of the cycle, it gives that exact same energy back to the source. So the net consumption over a full cycle is 0. It just borrows and returns.
Chalo, let's quickly summarize all the important points from our discussion today and also see how this topic connects to the rest of our chapter.
So here are the 5 key takeaways for your revision. First, an inductor has inertia. It opposes the change in current. Second, because of this, the current always lags the voltage by exactly 90 degrees. Third, this opposition is called inductive reactance, XL, and its formula is omega L. Fourth, unlike resistance, this reactance gets bigger as the frequency increases. And fifth, and this is very important, a pure inductor consumes 0 average power. And that brings us to the end of our topic for today. So I'll leave you with a final question, just to connect this to what's coming next. We just learned that in an inductor, the voltage leads the current. Now, we all know that inductors and capacitors are often treated as opposites in AC circuits. So, what do you think a capacitor does to the phase relationship? Give it some thought, and we will explore that in our next class.